Hello everyone. In the last video, we discussed the number systems and how to convert from different number systems to decimal. In today's video, we will continue by learning how to convert between the different number systems. Before starting our today's lecture, I just want to remind you with this slide, a slide that we discussed in the last video. I told you that if you want to convert from any number system to decimal, you need to apply this rule. And this rule says we multiply each digit by its positional weight, and then we do summation for all of these values together in order to get a number in base 10, in order to convert from here to the decimal system. In today's video, I'm going to do the opposite. I'm going to convert from decimal to any number system. We're also going to discuss other types of conversions, but this is our start. In the last video, I also told you that our focus will be on these four systems: the binary, the octal, the decimal, and the hexadecimal. And because we need to convert from here to here, so we can start explaining how to convert from decimal to binary. The method that we use to convert from decimal to binary is called division and multiplication. And by the way, this method can be used for any conversion from the decimal to any number system. So we can use it to convert from decimal to binary, from decimal to octal, and from decimal to hexadecimal. It consists of two steps. In the first step, we apply a series of divisions. In the second step, we apply a series of multiplications. So, in the first step, we divide the integer value of the decimal number by the base value. And the base here refers to the base of the system that we are converting to. Here we are converting to the binary, and the binary base is equal to 2. And that's why here in this case, we are dividing the integer value by 2. And from this step, we use the remainder as a result for our conversion. I'm going to explain how by an example. In the next step, we apply a series of multiplications on the fractional part. And we multiply here by 2 because, again, our binary has a base equal to 2, and that's why we are multiplying by 2. Here I forgot to write something. I hope that you write this on your side. From this step, we take the integer part or the quotient. So from here we use the remainder, and from here we use the integer part. I'm going to explain this by an example because it will not be understood without the example. So this is our first example. The value is 20.625 in base 10. So let's explain how to convert this value or this number from decimal to binary. Let's apply the first step. Let's apply a series of divisions on the integer value. The integer value here is 20. So I'm going to take the 20 here and write 20 and then divide this value by 2. 20 divided by 2 is equal to 10, and the remainder is 0. 10 divided by 2 is equal to 5, and the remainder is 0. 5 divided by 2 is equal to 2 with a remainder 1. 2 divided by 2 is equal to 1, and the remainder is 0. And then 1 over 2 is equal to 0, and the remainder is 1. We stop here because if you take this value and divide it by 2, the values will be zeros, and these zeros will be on the left side, so they are worthless. We don't need them, okay? So here, so we have the remainder here. And I told you from this step we use the remainder. But the question here is, this value will be on the right side or on the left side. And the same applies to this value. We call this value the LSB, the least significant bit. And this value is the MSB, the most significant bit. I already explained these two terms in the last video. So the most significant bit refers to the last bit on the left. and it is called most significant, most important, because it has the largest weight. If you remember, the weights of the positions are starting by 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. Let's say 2 to the power of n. So this is called the MSB because it has the largest weight. And this one is called the LSB because it has the smallest weight. So here we can write this like this. We can say that 20 in base 10 is equal to, this is the MSB, so it should be on the left, right? So should be 1, 0, 1, 0, 0 in base 2. So this is the solution to the integer part. Now let's work on the fractional part. 6 to 5. As I mentioned here, we need to multiply, not divide. So we need to multiply the fractional part by 2. So multiply this by 2, this is equal to 1.25. And as I mentioned, from this step we use the integer part or the quotient. So I'm going to take this one here. And then we use only the fractional part here. So 0.25 multiplied by 2, this is equal to 0.5. In this case, the integer part is 0 and the fractional part is half. So multiply half by 2, this is equal to 1.0. So the integer part is 1, and we stop here because no need to multiply the zeros and continue by multiplying zeros. No need to do that, okay? So this is the result. But again, in this case, by the way, it doesn't matter if you put this on the right or on the left because it will be the same. But this one is the opposite of this one. So if this one here is the LSB, then this one is the MSB. That's it. So we can say that 0.625 in base 10 is equal to this one first, and then 0, and then 1 in base 2. So the final output here, this value in base 10 is equal to, okay. So we can just remove this. We need to write this value 10100, 10100. I put a distance between the numbers. I'm doing this for a purpose, but just don't worry about this for now. By the way, I forgot to write the binary point here. Okay, so I have to write the binary point here. And then we write the binary point and then 101. 101. This is in base 2. So this is the result. And the question here is there a way that we can confirm that our result is correct or not? The answer is yes. And the answer is explained in the last video. I explained it in the last video. We can convert this number back to decimal. How? All you need to do is to write the weights. So this is 1, 2, 4, 8, 16. And this is half. This is quarter. And this is 1.25. And then add all values that has 1, because we multiply each digit by its weight. The zeros will give zeros, right? If you multiply 0 by any value, it will be equal to 0. So we multiply 1 by 16. So it is 16 plus 4 plus, so let's say, it is 16 plus 4 plus 0.5, this one, plus 0.125. If you add all of these values, it is going to be 20.0 625. So our result is correct. That's how you can confirm that your result is correct or not. So this is our first example. Let's go to the next example, 39.125. Let's remove all of this, and here this is the integer part. So let's divide 39 by 2. This is equal to 19 with a remainder 0. 19 divided by 2. This is equal to 9 with a remainder, sorry. The remainder here is 1. The remainder here is 1. Then 9 divided by 2. This is 4 with a remainder 1. 4 divided by 2. This is 2 with a remainder 0. 2 divided by 2. This is 1 with a remainder 0. And then 1 over 2. This is 0 with a remainder equal to 1. Again, this is the LSB and this is the MSB, so we can write 1, 0, 0, 3 ones in base 2. This is equal to 39 in base 10. Now let's work on the fractional part. Let's multiply 01.25 by 2. This is equal to 0.25. So we take the integer part here and then 0.25 multiplied by 2. This is equal to half. We take the integer part, half by 2. This is equal to 1. And we take the integer part, which is 1. We don't need to continue because the fractional part here is equal to 0. And again, this is the MSB. So we can write 0.125 in base 10 is equal to 0.001 in base 2. So the final result is this value is equal to 100 ones, 100 ones, and then dot 001, 001. If you want to confirm your result, you need to write the weights. So 1, 2, 4, 8, 16, 32. And then this is half, quarter, 0.125. You don't even need to write the equations. You can just add 32 plus 4 plus 2 plus 1. If you add 32 plus 4, this is 36, 38, 39. And the fractional part is 0.125. So our result is correct. So this is the second example. Now we know how to convert from decimal to binary. Let's go to the next step, how to convert from decimal to octal. We apply the same steps using the same method, the division and multiplication. So here we divide the integer value by the base value. And here we are converting to octal. So we're going to divide by 8, not by 2. And as I mentioned in the previous slides, we use the remainder from this step. Here also, we multiply the fractional part by 8. Let's solve the two examples that we explained in the previous two slides. So 20.625. So 20 over 8. This is equal to 2 and the remainder is 4, right? Because 2 multiplied by 8, this is 16, and 20 minus 16, this is 4. So this is the remainder. And then we take 2 and divide it by 8. This is equal to 0, and the remainder is 2. So we can say that 20 in base 10 is equal to 24 in base 8. Now let's work on the fractional part. 0.625 multiplied by 8. This is equal to, I really don't know, so let's try this on the calculator. So 0.625 multiplied by 8, this is equal to 5.0. We take the integer part, which is equal to 5, and then we have the fractional part equal to 0, so we don't need to continue. So we can say that 0.625 in base 10 is equal to 0.5 in base 8. So the final result is this value in base 10 is equal to 24.5 in base 8. This is how to solve this problem. Let's take another example, the 39 example. This one. So we divide 39 by 8. This is equal to 4, and the remainder is 7. By the way, if you don't know how to do this, because sometimes you might get a very large number, larger than 39, so you can do this. 39 divided by 8, this is equal to, let's write this here. This is equal to 4.875. Take the 4 and write it here. This is the result. And then subtract the 4 from here, so the result is 0.875. Multiply this by 8. This is going to give you the remainder. So multiply by 8. First, let's subtract 4 and multiply by 8. This is equal to 7. This is how to get the remainder if you don't know how to do that. So 39 divided by 8, the result is 4 and the remainder is 7. We take 4 and divide it by 8, the result is 0 and the remainder is 4. So that means that 39 in base 10 is equal to 7 in base 8. Let's take this value, 0.125 multiplied by 8. This is 1 over 8, so this is equal to 1.0, I think. So we can take the integer value here, and the fractional part is 0, so we need to stop here, and we need to say that 1.25 in base 10 is equal to 0.1 in base 8. So the final result is this value in base 10 is equal to 47.1 in base 8. If you want to make sure that your result is correct, put the weights. We are converting to octal, so the weights are 8 to the power of 0, 8 to the power of 1, 8 to the power of minus 1. This one, 8 to the power of 0 is 1, this is 8, and this is 1.25. Multiply each digit by its weight. This is the first rule, if you remember that. So 4 multiplied by 8, this is 32, plus 7 multiplied by 1, this is 7, plus 1 multiplied by this value, it is the same value. Add these values together, you will find that this is 39.125, so our result is correct. So this is how to convert from decimal to octal. Let's see how to convert from decimal to hexadecimal. Same example. Here we divide by 16, not 8, not 2. So let's work on this. So I'm going to take this value, 20, and divide it by 16. This is equal to 0, and the remainder is 4. So we don't have something else, right? Sorry, this is equal to 1. This is equal to 1 and the remainder is equal to 4. And then 1 divided by 16, this is equal to 0 and the remainder is 1. That means that 20 in base 10 is equal to 1, 4 in base 16. Let's work on this. 625 multiplied by 16. 0.625 multiplied by 16. This is equal to 10.0. So we take the integer part, which is equal to 10, and then we stop here because the fractional part is equal to 0. In hexadecimal, we don't have something called 10. Instead, we have A. So we write here A. You write it like this in the exam. So the final result is this value in decimal is equal to 1414.A in hexadecimal. Let's again write the weights and make sure that our result is correct. Sometimes we might write something that is not correct. So this is 16 to the power of 0 is equal to 1, and this is 16, and then this is 1 over 16. So 16 plus 4 plus A over 16. A is 10 and this is 16. Those values together are 20, and then 10 over divided by 16, this is equal to 625. So our result is correct. Let's take the next example, the 39 example. So 39 divided by 16, this is 2, and the remainder is 7, I think, right? So 39 divided by 16, this is equal to 2.4375. So the result is 2 minus 2 here. So we get 4375. Multiply this by 16. This is the remainder. So if we subtract 2 and then multiply by 16, the remainder is 7. So this is correct. And then we divide 2 by 16. This is equal to 0 and the remainder is 2. So 39 in base 10 is equal to 27 in base 16. And again, let's apply this here. 01.25. Yeah, this is 7. That's correct. Multiplied by 16. I think this is equal to 2. 01.25 multiplied by 16. This is equal to 2.0. So we take the integer part and we stop here because the fractional part is 0. So we can say that this value is equal to 27.2 in hexadecimal. Again, let's make sure that our result is correct. This is 1 and this is 16 and this is 1 over 16. So 2 multiplied by 16, this is 32 plus 7 plus 8 of 2 over 16 is equal to 1 over 8, and 1 over 8 is equal to 125. So the result here is 39.125 in base 10, which is correct. So now we know how to convert from decimal to any number system. This is a simulator that shows the steps to convert any value from decimal to any number system. I created this simulator by Gemini, and I am doing this because I only explained 2 examples in the slides, but I need you to practice. And you cannot practice without having a reference to compare your results with. So let's say you have this value and you converted this value from decimal to binary, octal, and hexadecimal. And you want to make sure that your steps, every single step is correct. How can you make sure, how you can revise this? You can do this by the AI tools, by the way. This is very easy nowadays, but this is another way to make sure that your steps are correct. So here we write the decimal value, the input, and from here we choose the precision, and I'm going to explain what do we mean by the precision. And here you can choose the system in which you are converting to. If you want to convert to binary, octal, or hexadecimal. So you can choose here which system you want to convert to. And here you will see the steps. So for example, let's take this value. Let's click next step. As you see, we divide the integer part, here the integer part, and this is the fractional part. For the integer part, we divide 15 by 2. The quotient is 7. The remainder is 1. Let's go to the next step. We should divide this value by 2 and see the result. So 7 by 2, the quotient is 3, the remainder is 1. Again, 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 okay? So now we finished the integer part, and the output here is 1, 1, 1, 1. For the fractional part, we multiply by 2, and then, so we take the value here, the integer part or the quotient, and then we multiply the remaining part here, 0.25 by 2, and here we take the quotient, which is equal to 0. And again, we apply the same. So as you see, we don't need to apply this step, so this will not be continued. And this is the final result. 15.625 is equal to 111.101. Okay? This is how it looks like. Yeah, when we say this is the LSB, this is, yeah, the MSB. Anyway, so this is how it looks like, and then we can choose to convert to octal. So let's see the first step. Divide this by 2, the quotient is 1 and the remainder is 7. So we divide 1 by 8, not 2. By 8, this is equal to 0 and the remainder is 1. So 15 in decimal is equal to 17 in octal. And then we go to the fractional part, multiply this by 8, this is equal to 5. We take the 5 here, this value is 0, the fractional part, so we shouldn't do anything here. And the final result is 17.5000. Why it is continuing here, although we have a fractional part equal to 0? Because I mentioned here that the precision is 4 digits. So precision means the number of digits on the right of the decimal point of this point here. So we need 4 digits here on this side. That's why it finishes 4 steps here, even if we don't need the last 3 steps. But if you write here something like, let's write something here. Let's look at something like that, okay? And let's convert this to binary. First step, there is no problem in the integer part, right? So 17 divided by 2, 8, and this is equal to 1, and then you can apply the same as you see. For the fractional part, we multiply this value by 2, and then we take 0, this value by 2, and then we take 1, this value by 2, and then we take 0, this value by 2, and then we take 1. As you see, it stopped here, although the fractional part is not 0, because the computer is limited. Each location has a limited space. It cannot be an open space. It cannot be like, for example, 1000 bits. It has to be 32 bits, 64 bits, 8 bits, and so on. That's why we have to determine the precision. Here it is very small. It is 4 digits only. But as you see, when you choose 4 digits, you have to stop here. If you choose, for example, here 8 digits, you can continue another 4 steps. But that doesn't guarantee that 8 steps or 8 digits will make the fractional part is equal to 0. Sometimes it is not. Sometimes you need even unlimited number of digits to fulfill the fractional part, like this case, okay? So, by the way, in this case, there is something called error. Why there is something called error here? Because, let me show you. This value here, if you write this value, this is half, this has a weight of 0.25, 0.125, and this is 1 over 16. 1 over 16. If you add this value to this value, the output will not be 0.33. The output might be something like 17.29. I don't remember. So let's do this. Let's add these two values. So 1 over or divided by 16. So 1 divided by 16 plus 0.25. This is equal to 17.3125. So our result here is not exactly 17.33. It is 17.3125. Why it is not equal to this one? Because we stopped after 4 digits, after 4 steps. We didn't continue the conversion. That means we are removing part of the precision. We are decreasing the precision. And you can calculate the error by subtracting the original value, 1733, minus this value, and get the error value. If you increase the precision digits from 4 to 8, the error should decrease, and so on. So this is how the simulator works, and you can apply the same on the hexadecimal. You can try the hexadecimal, but let's see. We can try larger example, larger value. Let's see 33.33. So let's divide this. For the integer part, it is very easy. For the fractional part, I think it is also going to take some time. So the output is this, 21.547a. And also we stopped after 4 steps, and that means that this value is not exactly this value when you convert this back to decimal. You can use this simulator so that you can track your steps and make sure that each step here and each step here is correct. And that's all for today, and see you in the next video.